Okay, so now let's look at the arrangement of memory and data that goes on in association with RDBMS or whatever database system that you have. So if we look at the computer memory architecture, so we have CPU, then we have the cache, and then we are going to have the main memory. Then you are going to have the hard drive or the disk, and then you are going to have tertiary devices like tape backups or something like this. Okay, so this is how, in this direction is request going on, and in this direction is response going on. Okay, so what we are going to look at is how things go on in this main memory today, okay, and how things go on in here. Okay, so if we think of a disk drive, so this actually, if you think of the time frame, recovering data, there is an example in the book. Recovering data from the memory, main memory, it takes about 90 nanoseconds, and from the disk it takes about 30 milliseconds. So there is a huge, 3 orders of magnitude difference in the time frames that you're looking at. So just to get the perspective of the time frame difference. So now, actually, no, 6 orders of magnitude. It's nanoseconds, milliseconds. Yeah, 6 orders of magnitude. Okay. So what you have is, what happened?
That's a lot.
Yeah. Okay. Good morning. Okay. So if we think of a disk drive, what you have here is you'll have, these are the heads that will read the tracks on this disk. My diagram is okay to visualize, probably to actually not. And so the disk has tracks on it, and on tracks now the data is arranged in blocks. Data is arranged in blocks. So what you have is, so you have blocks here, and these heads are going to seek the track where the data is, and then this disk is going to rotate to actually position it on the block, and then the read occurs. So the total time is going to be seek time plus then it is going to rotate and then transfer. So that is the whole. So when people talk about a disk drive of 5400 RPM, right, or 7200 RPM, that is where these differences come into play. Or you think of these, like laptop drives are like 4200 RPM, or so those things actually improve efficiency rather than just thinking about the space also. So they become more expensive. Okay. So why is a database performance related to the disk? Is because the database, all the things that go on with the database, all the data must be in the memory. Database is not going to work on anything that is on the disk. It has to be fetched to the memory. That is why these things become so one part of database, DBMS actually, is going to go in and fetch this data, make it available in the memory, and then all the operations will go on. Okay, that is why there is a very intricate dependence on performance of the disk with the database. Okay, so now, because that is the case, now let us think of how efficiency can be improved in accessing the data from the disks, because now we know they are interrelated. So that is where the term RAID comes in. And so this is now of independent disks. So what is happening is, what you do is, if you have a data file, you can break it up and put it on different disks, so when you fetch it back, all these 4 can be read together at the same time. Okay, so what you do is, your access time becomes as if you were just accessing from one disk. Okay, so you get a huge improvement in performance. Okay, you suddenly increase the bandwidth of transferring data from a disk. Otherwise, you would have the bandwidth of only one disk to transfer the data for you. The problem occurs is, when you do something like this, is you increase the chances of disk failure. Because now, probably, you have a question?
Are they read actually in parallel, or are they
parallel? They're read parallel. So that is the only way we'll get the efficiency improvement. If we are not able to read it parallelly, then if we are going sequentially still, then it is the same thing doing, because then what you're doing is, you're actually using the bandwidth of one disk, then going to the second disk, then going to the third disk. So it is the parallel reading that is what gives us the cumulative bandwidth of transfer. So now, so what was I talking about? About failure. Okay. So now what is happening is, the moment you put in 4 disk drives, you increase the probability of any of them failing. Okay, because now you have a much higher probability of either of these 4 will fail. So that is where, so now what you have to do is, you have to strike a balance between performance and stability. Okay, so there are several different RAID configurations which leverage one or the other depending on what is your priority. You can do one or the other, like 6 or 7 are mentioned in the text, and you can look at it later on. But now let us see. So this process of actually breaking up the data into different chunks or different parts is called data striping.
So are you saying the data striping is referring to segmenting it across multiple disks? I thought it was on one disk across the various platters of the same disk.
No, it's on different, because if it was on the same, then what is going to happen is, you have only one disk controller. How would you move?
The term data striping referred to the way that.
Can you, if I'm wrong, can we confirm it? I could be wrong. I just want to make sure.
Do stripe the data across all the various platters so that they can read
Why?
and write all the platters at the same time.
Oh, they can't. No, they cannot read and write all the platters at the same time, because it is very difficult to sync the movement of heads. I mean, there are some right now, very recent technologies have come up, but they still are very unstable. To do like 2 heads in the same disk doing different tasks. Actually, can we look at that? Yeah.
Over multiple disks.
Yeah, but that technology, that technology is something that people are trying to get at, but it is still a big challenge, because that would be a huge, again, what you end up doing is incorporating everything in the same disk. It is a little hard, I think. What is it?
Yeah.
Okay, so, but that technology is something that, and I don't want to say it is not correct, because that technology is being used, like it is available, I should say.
Okay. It's just not mainstream.
Yeah, it is. That is what is my understanding. So, okay. Now, okay. So we did say data striping, and we divided the data. Okay. So now what we introduced was this. Okay, so we have introduced an inherent instability in our system. I should say instability. We have introduced it. Okay, so how do you then take care of that? Is then you have to make the data redundant. So then you start putting the data on same data in different disks again. Okay, so now what you are trying to strike a balance is how much of a performance increase I want and how much data redundancy I can handle. Okay, so that is where the intelligent decisions, depending on the situation, on your priorities of the system, is what you decide. Yes, John?
Can we just zoom out a bit? You started off saying the database is going to deal with everything in memory because of the 6 orders of magnitude difference with disk, and now we're on to RAIDs, which is a way to speed up access from disk. So what's the relationship? Okay,
let me say the reason why it was doing everything on the disk is, why the access to the disk is important is now DBMS actually has to go in and grab the data to the memory. So what we are doing by this is we are reducing that time. So in effect, we are improving the performance of our DBMS.
So there is constant interaction then with the disk in the database?
When a request is sent, yes, because then the disk manager and the buffer manager actually have to go in and load the data into buffer pool and make it available. I'll go a little bit more in detail about your question that you just asked later on. Okay. So one way to take care of how to actually then maintain the say out of these 4 disks, one crashes. Okay, now you have to regenerate this disk. You'll have to restore this disk, right? Because a part of this data was somewhere, this part was somewhere, this part. So you have to get this disk back. So what you do is you make a check disk. And this check disk, what it will do is, let me break this up. So let us think of these, and let us just say there are like D disks, okay? And the first bit is going to be either 0 or 1, right? Okay, so we can say in this example, I bits have value 1 and D minus I have 0. Okay, so either this I will be odd or even, right? 7 bits have 0 or 6 bits have 0. Only 2 values are there, right? So now in this check disk, we have this position 1. Okay, the value that will go in here, if I is odd, it gives you 1 value. If it is 0, it gives you 0. If it is even, it gives you 0. Okay, I think so. Yeah. So if I was equal to 6, okay, that out of these D drives, D bits, the first bits, 6 of them have 1 in it. Okay, so this value will be given 0. Okay, now this disk, so this, let us assume this was 1, this crashes. Okay, now you'll go back here and you will count the parities here, and then you can regenerate that bit using the value that was inserted here. Because if now the count came out to be 5, you know it was 1. Okay, so this is the check disk that actually keeps track of the parities.
There's 1 bit for each field.
Yeah. Okay, so this is one way. There are other ways also. There's one more way that the book mentions, but this is the most accepted way to maintain the check. Okay. Yeah.
I've never worked with a machine that had a configuration like this. I'm not exactly clear exactly what kinds of crashes you'd be dealing with and sort of what the real implications of recovery is. Is it that, like, you know, if one of these things goes bad, is it simply that something becomes corrupt and so the machine itself sort of pauses for a moment and kind of regenerates it? Or are we talking about a disk just kind of like, you know, burning out or something and having to be replaced?
It's the second part. It's the second part,
so
and
you have to call some guy to come in and put in a new disk and run some big utility to, you know, to get everything.
Exactly.
Again.
Yeah.
So
That and actually,
sort of like a big
yeah, and it actually is not very uncommon. It is really not uncommon. I mean, especially when you are talking about big RAID devices, it does happen.
So your server is still going to be out of commission for the afternoon while you guys do this?
Till you recover. Okay. Okay. So I'll just give one example of. So the whole idea with RAID devices is that you have to decide the trade-off between performance and redundancy. Okay, if you're just talking about pure performance, you should just break it into 4 with 0 redundancy. Okay, that is level 0 RAID. Okay, but then you might have heard about term mirror disks, like you want to have, if you have a database and you'll have a mirror on the other one. Like usually, even if you are running at home your own server, like your own website, it is always a good idea to mirror the whole disk. Okay, so you can set up your database to actually, so that would be now, so this is level 0. Okay, in which you just do data striping and get the best performance. Okay, in level 1, what you will do is you'll have the mirror disks, total copy. Okay, you don't do any striping here. Okay, but what you have is, it won't die because you can recover the whole thing back. But when you are writing, then you have to write on both. So that is those. So then there are other combinations of these where you have level 1, 0 and level 0 plus 1 and very small differences that are all mentioned in the book. So when you are reading through it, you'll know what. Because when it really becomes relevant when you are actually deciding what should be for your system and then looking into what architecture of the hard drives you want to keep. So that's that part. So now let us look at where actually all this go in the big perspective of DBMS, and that would actually give an idea about response for John's question. Yeah.
When you do the mirroring, do you need that checksum system?
Yeah. Then you will need that. Yeah. Because you have to. How else would you sync everything?
I thought we have just 2 copies of it. Yeah.
How would you then?
It's a check disk. You just have,
If one fails, you just copy it over.
yeah, you just have one drive and another drive that looks just like it. You don't need to.
No. Then how would you sync the writing? Oh, you mean check disk?
Yeah.
The parity, that parity bit thing, that scheme.
That is only needed when you actually break the data. No, I'm talking about how to sync it. I totally use the term checksum, not check disk. That's why I got.
Oh, checksum is the. Oh,
Yeah, that's so check disk you don't need till you break the data, right? Because that is when you are using the bit values and then regenerating that thing. So in this we don't.
You don't need it in the mirroring.
Yeah. Okay, so let me draw a diagram of what we are just talking about. And then here there is that query processor and the request coming in from the top. Okay, so now what we'll talk today about is how these two work, the buffer manager and disk manager, okay, to actually do the whole DBMS part, interaction with the database. Okay. So disk space manager, the functions of disk space manager are that it is going to define how big is the unit of data, okay, it will be called page and it will be called block at times, okay. Then it is going to tell you how it will provide the commands for read write, allocation and deallocation. One more question I wanted to ask. Do you guys, are the handouts useful to you guys? Because then I would start, in the second lecture actually, because of the network down, I didn't print and then we continued like this. Are the handouts useful to you? Then I can actually give them out also. Okay, I'll do it then. Okay. And the third thing is that when it decides the size of the page or the unit of the data, it will be called a page, is what will become the block on the disk. Okay? So it has to keep track. Let me see a diagram I made. Where would it be? Yeah. The most important part is it has to keep track okay, it can keep track of used or unused blocks either by doing a bitmap that you can toggle between 0 or 1, used, unused, or it can keep actually a linked list of used blocks or unused blocks. So you can then start, you know where actually the unused blocks are, and you can start using them. The main role that comes for buffer manager is that now this buffer manager actually has to bring the page from the database to the memory. Okay? So buffer manager's role are to bring the page to memory, decide. So now what is happening is, so you have this memory here, and constantly pages are being requested here. They will have to be brought in and released. So this is a very important decision process, that what page should be made available in the memory for this program to access and for how long. Okay, that is an important task that buffer manager does. Okay. What it does is it will create this memory and divide it into the size of the page, and this would be called buffer pool. So it divides the whole memory that is available into buffer pool, and then some of these buffer pools will have the page that is already there from, say, this is like a snapshot, that this is a disk page from the disk. and some of them will be empty, and basically a distribution here. Okay, so now this buffer manager has to make decisions. What page needs to be fetched, where it will be put, if it is fully occupied, which one should be released so that the next one can be put in, or if there is none of them that it can release, it has to abort the transaction because it can't bring another page into the memory. So what it does is it actually, I made another diagram, yeah, here. Okay. So what it has to do is it actually works through a replacement policy, which is very well defined, and then it defines certain attributes for each buffer unit to decide whether it should be released or it should be kept there. So what it'll do is it'll give you two attributes. So now I'm looking at one of these. Okay. This will have a variable pin count, and will it have reserved in this? No, it has to have, okay, so pin count and whether this is dirty. So now it has two variables, that there is a pin count, and pin count is how many people are using this page, have they requested this page. And every time they release, so there may be 10 people who are requesting this page at this time, so this pin count will take the value 10. And as they release this page, this will keep on decrementing. So till it becomes 0, it knows it is being used. Okay, so it keeps track of this pin count to make sure not release this page or release this block free till the pin count becomes 0.
So is that like a handle?
Yeah. So that is where the idea of actually, and that is where actually, I'll come to it, that is where the abstraction of controlling transaction also comes, because there may be 5 people trying to change the same, they are accessing it and they are trying to change it also at the same time. That is where you do the lock modes and all that.
So that's all on the buffer?
No, that is done by, concurrency manager, but at the buffer level, exactly. Yeah. Because what it has to do is, okay, just give me a little time to get into it, otherwise we'll lose the sync. So all that gets decided by this variable. When something writes, it toggles the dirty on. Okay, so now if you want to say this is 0 and dirty is on, so then this buffer manager has to communicate, write the changes when you release it. Okay, because now this page has changed since it was accessed. So it has to be written in a different state to the database before it is refetched or accessed again. Okay, so let me just summarize this with the sequence of steps. I'll keep this here. Okay. So we have a request. So once it has read the requested page, it is going to go back and return the memory address of the page that was requested. So now what happens here? So the big issue comes, how do you do this? Okay, this is where now you have replacement policy implementation. Okay, so the buffer manager is going to have a replacement policy. That is where your question will come in. And what replacement policy would do is you can have in two ways, which is least is LRU, least recently used page. What you are going to do is you will start creating a queue of all the free pages, okay, and as they become more free, you put in the back and you start taking it from here. Okay, so this will happen only when the pin count variable is equal to 0. So as they keep becoming free, now you know where this whole link, this structure is, where is the address for the first one, and then the links to the next pages, and so you can keep on allocating these, so you can find out. The other way is, it is called the clock implementation. In clock implementation, you have another variable called referenced. In the clock implementation, it is the same. Fundamentally, it is the same, least recently used. But what you have is, think of it as a circle where all these pages are there. Now a variable current is here, whose value right now is, say, x. It will go here and it will check. If the pin count is 0, so first state, actually I should draw this. Can I erase this part? Because I think this is an important concept. We'll summarize the. So I'll draw this. Page retrieved, then we go back and finish it. What happens when we don't have, so this is page in memory already, so it is going to check if it is already in memory, it is just going to return. If it is not in the memory, then it is going to say, okay, that means I need to get it from the disk. Okay, so not in memory. But before it has to go, it has to actually find a replacement frame. If it finds it, then it replaces it. Otherwise, if there is like all the frames are occupied with no pin count 0, then either you keep on waiting or abort the transaction. If it is a transaction, then abort it, because it just can't bring the information to the memory to do the transaction. Otherwise, what you do is, frame is available, with pin count 0. The moment it finds this, it is going to check the dirty variable, and if dirty is 0, then it just fetches the new page in this. Otherwise, it is going to write and then come back here. Okay, it got the page and returns the address. Okay, now let us look at where this thing comes in. Okay.
When you say there to wait or abort, I mean, it doesn't have to be that passive, right? It can ask another part of the system to generate an empty frame replacement.
But it has already used up, it has used the memory that it had.
And there's no way to release.
That is the, yeah, because it didn't find, this will happen only when it can't find pin 0, right? Because,
Assumed that it's been
yeah, it is going to search for replacement frame. That's, but this is, so this is a very important process that I'm going to now explain about your question, how actually it finds out and how it makes it available.
Could you specify a little bit more how the pin count is calculated? And I mean,
Pin count is very simple. Yeah,
who's using
exactly. How many requests are there?
specifically what is the who is using?
So if suppose you write a code and you are accessing certain piece of data, that data piece is a part of page, because there is a certain big block in which that data was existing. Now that whole page has to be brought into this frame, and it is there. At that time, a second request comes in for something in the same block. It may not be the same data piece, but the same block, right? So now what is happening is it sees this, and now it is in memory because you were using it. So it knows that it has been requested. It will increment the pin count to make it 2. So now there are 2 users who are accessing it. So, and when you'll release it is when it is going to start decrementing it.
What specifically causes it to be released?
You call it, you release the handle on the whole, your own data set that you called for.
Okay.
Right? Because you are, so it is, that is where also explicit release is much better. I think there must be some time-based released also built in, but either it will be database dependent, or actually I'm not aware of what exact is, otherwise I would have told you. I can find out if you guys want. We can, at least I can look into Oracle. I'll do it. I also want to know now. So I'll look into Oracle at least how it does the handle management, and it would be a nice document. Yes, I'll send it to Mike B. This I can say on our recording. He's the man. Mike Brizik. Okay. So we are looking into this. So this is the current frame. So let us again look at like this representation where right now our current frame is here. The variable current is pointing here. So we are at the current frame. If the pin count is 0 and the reference would be with E or without E?
With the
Okay. Okay. So if reference can have 2 states, on or off. Okay. So if referenced is equal to on, then people have stopped using it. Okay, there is nobody who's requesting this, but it being on means that it was very recently asked for. Because when this variable loops over this circle, its job is that if it is 0, because when you are requesting this page, we are not doing anything with this count. So when you release it, or reference, sorry, when you release it also, you don't change the state of this. It still stays on because it was being used, but now there is no user. So this event is going to toggle it to off and still leave it there because it knows that it was very recently used. So let us leave it there. Okay? But now it is off, so it has been toggled to off. It will keep on going. The current will get incremented to the next, and it will keep on going. If it finds another one which has count 0, and it is off, it is going to replace it.
It's is random if there's more than one of those.
Yeah, so whichever it will hit first.
Not random, it's
I mean, it is still going in a circle because it is incrementing thing. So what you are seeing here is that, let us assume it did not take this one, even though the count was 0. What it did was it turned this off, and if it did not find any of the other ones with this state, when it hits back this, it is going to take it. So this is how this system of selection is working. Which frame to take, how to take it.
But if in the meantime, while it's tripping around the circle, it had been referenced again.
Yeah, so then it'll, yeah, exactly, because it will be toggled on. Okay? Okay. So that actually completes the discussion of how actually these two things work and how data actually is fetched into the memory and how disks are arranged. Okay. So that should help you finish the assignment for chapter 7. There is no assignment for chapter 8. I would really encourage, and I want to make sure in the recitation, just different types of RAID configurations are discussed. Okay? Yeah.
If you want to put a RAID disk set in your computer, do you need a special operating system? Or just...
I think you have to, with Oracle, you need to specify the configuration of your device.
Oracle handles it itself? Handles all
When you set up,
Motherboard a lot of times needs to be RAID aware.
but you'll need 2 disk controllers, one thing, right? And then you have to configure your DBMS to actually write the 2 times every time you do it. So Oracle has the functionality.
The database likes to have, it doesn't use the operating system.
Yeah, for any file. Yeah,
It has its own.
But the operating system still has to know it's there.
Oh,
yeah. So device controllers have to be there, and I think motherboard has to be
If your
aware.
motherboard's not RAID capable, you can buy things to upgrade for an old
Okay.
motherboard.
Okay.
Generally, you would have it
But,
in
yeah,
your
Maybe
You
plugins.
can compile Linux kernel to deal with RAID, and I'm sure Windows 2000 does the same.
Okay, so I am here now to talk about projects, one thing. Second is please catch up on your assignments. Okay, so tomorrow and the next 2-3 days will be a lot of real understanding of indexes, and it'll be much more involved. So please, till now it was quite subjective. Now we'll actually understand much more of how actually to